first question is in an afterburner of the turbojet engine. Basically, okay, the question is so I get these questions from the previous session that was held in this thing. Okay, so the first question is on the afterburner, the fuel is additionally injected. Is it injected twice in the combustor, or before the nozzle, or in the intake, or in the turbine? So do you know where is the afterburner placed exactly in the turbojet engine? No? Oh, okay. So, right. So this you must have seen the schematic of turbojet engine. What is the first component? So there is air inlet, yeah, and before the compressor you have this diffuser, that is this area is expanding, so that is acting like a diffuser. This is a compressor. Then you have a combustion chamber over here, right? And then you have a turbine, and the turbine and the compressor are basically connected to each other, so the turbine is going to run the compressor, and then what you have is a nozzle. Now sometimes what we have before the nozzle is an afterburner, which is essentially a region where combustion occurs. Okay, so over here you will have an afterburner. So the answer to this question is before the nozzle. Okay, so the next question is for a constant cross section duct having Rayleigh flow with thermal choking, the Mach number at the exit of the duct is what? So what is the key word here in the question? Choking. So last session we discussed what is choking. So what is the answer here? Anyone? Okay, last time we discussed that choking is nothing but when Mach number in the throat of a nozzle or in a duct, essentially the Mach number reaches 1, right? So here the answer is equal to 1. And what happens when Mach number reaches 1? So say for example you have this nozzle and at the throat Mach 1 is achieved, then whatever changes you are making in this upstream flow, that is not going to reflect in the downstream flow. So basically even if you change the mass flow rate here, then only the pressure in this upstream flow is going to change, but the pressure in the downstream will not change. Okay, right, so then the next question is, for a given Mach number, the thrust and the specific fuel consumption of aircraft engine, whether it increases or decreases with the altitude. So here there are two questions. One is regarding the thrust and the other is regarding the specific fuel consumption. So remember we had this plot last time. This is say your thrust, and on the x-axis you have the altitude. Yeah, so can you tell me how this is going to vary? Am I still audible? Okay, so how is this going to vary? Alright, so how is a turbojet supposed to function? Turbojet should ideally give you as much thrust as possible, right? And if you remember last time we have discussed that the turbojet will produce maximum thrust when the exit pressure PE is equal to the atmospheric pressure PA. Now if there is any difference between these two pressures, then essentially your turbojet is not functioning at its full capacity. So what happens as you increase the altitude? Say you have designed your turbojet engine at sea level. Okay, so you have designed it for sea pressure, sea level atmospheric pressure. Now as you increase the altitude, the atmospheric pressure is going to reduce. So then because you had optimized for sea level, and if you start flying at higher altitudes, then the thrust is simply going to decrease. Does that make sense? Okay, but then if you have designed it for a higher altitude, then what will happen? Say if you designed it for some altitude like 35,000 feet. Okay, I just gave the answer, right? Say for example, you have designed it for some pressure P, PE, right? And that equals PA at some altitude H. So up to that altitude, your PE is actually going to be the atmospheric pressure. Say for example, at this altitude you have designed the turbojet to be optimized at this altitude. Now if you are at this lower altitude, the atmospheric pressure is higher than the design pressure, so the exit pressure is going to be more, right? So as a result, you are going to get more thrust. Yes, it's going to be increasing and then it's going to be decreasing, but the specific fuel consumption, that will keep decreasing. Okay, so the answer here is increases and decreases. Yeah. Okay. So this is, the question is kind of ambiguous here, so I would just like to tell you this graph rather than give you any of these options, because the question needs to be more specific about where the aircraft is actually optimized for operation. Okay, so moving on to the next question, what is the purpose of using afterburning process in a turbojet engine? So why do we use an afterburner? So like I said in the previous question, where do we add the afterburner? It is in the just after the turbine and just before the nozzle. Now what is the work of a nozzle? What does the nozzle do? Yeah, it increases the kinetic energy, it decreases the pressure. So now if the nozzle has to increase the kinetic energy, how does it achieve that? So we know that the velocity at the end of the nozzle actually depends on the turbine outlet temperature. So after the turbine, if you have very high temperature, then there will be a lot of thermal energy in the fluid, and that you can convert to kinetic energy, right? But what happens in a turbine? So if you go back to your turbojet cycle, you have this turbojet cycle is like this. In the compressor, in the combustion chamber, again the temperature is rising in the TS plot, but in the turbine there is a drop in the temperature, right? So what we do is we add an afterburner so that you can further increase the temperature to much higher temperature values. As a result, the expansion in the nozzle which will be much larger, and that will lead to much more increase in the kinetic energy. Okay, so what is the answer over here? The purpose of using an afterburner is to increase the turbine inlet temperature. Is this clear? Okay. Now in Rayleigh flow through a duct, when the inlet flow is subsonic, the stagnation pressure along the length of the duct, what happens to the stagnation pressure? What is a Rayleigh flow? So you must have seen the lectures, right? So what is a Rayleigh flow? Okay, do you know the SFE equation, the energy conservation equation? Okay, it's constant area, frictionless flow. What else? What else? Yes, exactly. So we assume that the duct is frictionless, okay, and you can assume it to be constant area or variable area, but the main thing is we account for heat addition or heat rejection. Okay, so this basically says, like in the combustion chamber, if you just assume that this combustor is like a duct where combustion is happening, so you are allowing for the heat addition in your energy conservation equations. So you can write the enthalpy equation, that is H plus Q plus W is basically constant, and here we say that any changes due to the work is 0. You are assuming there is no work, but this Q is non-zero. So in that Rayleigh flow, the question is, how does the stagnation pressure change? So when will the stagnation pressure change? Okay, what is stagnation pressure first of all? Oh, and these things actually we've been doing for 7 weeks now, so you should be able to answer this. Total pressure or stagnation pressure, how is it defined? Isentropically. Yeah, so starting from a static condition, you bring the flow to stop isentropically. So this is a assumption that we make, and this is essentially some reference quantity. Okay, so we are bringing the flow isentropically to a stop, and if we do so, assuming that we are able to do so, what state the system will achieve is called the stagnation condition, and the pressure at that condition is stagnation pressure, temperature at that condition is stagnation temperature. So now we started with some pressure P, temperature T, velocity V, and then we brought it to P naught, T naught, and 0 velocity. So now what is the equation of P naught? P naught is nothing but P plus rho V square by 2, right? Is this right? Have you seen this equation? Yeah, okay. So now the question is, how does the stagnation pressure change? Always remember that the stagnation pressure will change whenever there is any heat addition or whenever there are losses due to friction. Okay, so if you remember your, let me just add a page over here. Yeah, so if you remember the TS diagram of your turbojet engine again, so what we draw here in the TS diagram, we draw these constant pressure lines, isn't it? But these are constant static pressure lines. So you start, this is say P1 and this is your P2. So in the compressor, your static pressure increases like this, and then in the combustion chamber it remains on P2 because you assume constant pressure heat addition, and then in the turbine again there is going to be decrease in the static pressure, and then before the compressor you essentially have a diffuser. So the diffuser would, in the diffuser also we say that the static pressure is increasing, and in the nozzle we have the static pressure is decreasing, right? But now if I ask you what happens to the stagnation pressure, so if for example I drew this TS diagram, but on instead of drawing the constant pressure lines, if I draw the constant stagnation pressure lines, okay, so can you tell me what is going to happen? Say this is the stagnation pressure P naught 1. So I have started from atmospheric pressure, which is essentially the stagnation pressure. What happens in the diffuser? How does the stagnation pressure change? It is almost constant, it remains the same, because in the diffuser you don't have any work added, there's no turbo machinery over there, and of course we are assuming there's no heat loss or anything, so the stagnation pressure is going to remain the same. So I'll just for reference number this. So let us say there was this inlet. After inlet, up to the inlet of compressor, it is says 1, then you have 2, then this is 3, 4 and exit. Okay, so here inlet and 1 are essentially the same point, because I have considered the stagnation pressure lines over here. What happens if I go from 1 to 2? Will the stagnation pressure jump or will it remain same in a compressor? So what are you doing in a compressor? Yeah, so we are doing work and there is turbo machinery involved, right? So you are adding work to the fluid, so the stagnation pressure is going to increase. Okay, is that clear? And then the next assumption is that in the combustion chamber the stagnation pressure remains same. Now understand that this is a huge assumption which you are making, that a stagnation pressure in the combustion chamber is going to remain constant. Essentially, when you make this assumption, you are neglecting the Rayleigh flow. You are assuming that there is no Rayleigh flow. Now, in this week 8 lecture, we introduce the Rayleigh flow, and then the question is, what will happen to the stagnation pressure? What do you expect? So now you are adding heat. Can stagnation pressure increase or decrease in this case? Yeah, it will decrease. Why? Stagnation temperature increases. So what? So why will the stagnation pressure decrease? Mach number increases. In a combustion chamber, we assume almost constant velocity. Isn't it? Then why would the stagnation pressure change in Rayleigh flow? So you are adding heat, okay, but understand that in the combustion chamber or in a simple duct, if you are adding heat, you are changing the temperature conditions. You are adding energy which goes in raising the temperature. So your stagnation temperature will increase, but you will have losses, and that is why the stagnation pressure is supposed to decrease. So this is actually not intuitive, because you will say that I am adding heat. So if I am adding heat, the energy should increase, so the stagnation pressure should have increased. But instead what you see is that the stagnation pressure is going to decrease. Is this clear? Where does the heat that you have added go in? It goes in increasing the stagnation temperature. Okay? Is that clear? Should I move on? Okay. Okay, so now we'll move on to the big numerical for today. So here I have a twin spool turbo fan engine, which the parameters are given, that is the bypass ratio and overall pressure ratio, everything is given to you. In this fan, the fan is driven by a low pressure turbine, the compressor is driven by a high pressure turbine. So what is a twin spool engine. So you can see over here, for example, this twin spool engine, these violet blades over here in the turbine zone, they are running the compressor blades over here. Okay, so this is the high pressure turbine which is running this high pressure compressor, whereas the low pressure turbine is running the fan. And you can see that the shaft which connects between the high pressure turbine and the compressor, that is this violet colored tube kind of thing, and the shaft which connects the low pressure turbine and the fan is this green colored thing, and the green shaft is basically passing from within that violet shaft, right? So that is the twin spool arrangement. Okay, so now what are we given? We are given the overall pressure ratio, fan pressure ratio, bypass ratio, and the maximum temperature that is achieved, that is the turbine inlet temperature is given, which is essentially defined by the material of your aircraft, right? So and also you are given the polytropic efficiency, isentropic efficiency for all the components, and mechanical efficiency of the spool. So what is mechanical efficiency? Now while transferring the work from the turbine to the compressor, the efficiency of the spool is going to come into play. So this is nothing but the transmission efficiency. Okay, yeah, any questions? Okay, no. So combustion pressure loss, here we are assuming that some amount of pressure is lost in the combustion chamber, and then total air mass flow is given to you, fuel air ratio is given to you. Now what is total air mass flow? Remember, in a turbo fan engine, you are going to take in some air. Some of that air will simply flow from the outside, that is as a cold flow, and some of it will pass through the core of the engine, and that will come out as a hot flow. So we have a cold flow over here, m dot c, and over here we have a hot flow, m dot h, which is going through this entire core. And what is given to you is the total air mass flow rate that you are taking in over here. So this is m dot total which is given. Okay, then the ambient pressure and temperature are given, and so Cp and gamma for air and gas are given. So now we are asked to find certain quantities like thrust and the fan outlet temperature and so on. So what we have to do is basically solve the entire cycle for this turbofan engine. Okay, so yeah, I've just made a schematic here, as you can see. So there is cold flow m dot c and a hot flow m dot h. I hope this much is very clear. What is the bypass ratio definition? What is bypass ratio defined as? Yes, that's right. Okay. Okay, and usually this turns out to be, in practical turbojet engine, it is in the range of 8 to 12. Okay, so here what we are given, bypass ratio is of 5. So this is a small turbofan engine, in some sense. Okay. Okay, so again I have written these quantities, that is the polytropic efficiency of the fan, compressor and turbine is given, isentropic efficiency of the nozzle is given, and the efficiency of the spool is given. Now we are given two different things, Cpa and gamma A, that is the specific heat and the gamma value for air, and similarly for gas. So in the cold flow, see, the inlet is essentially just air and the cold flow is just air. So for the cold flow we will use these values, the air values, and in the hot flow, till the fluid moves through the compressor, it is just air, but in the combustion chamber we add fuel, right? So only after the fluid has come out of the combustion chamber, that is in the turbine and the nozzle, we will use the values for Cp and gamma value for the gas. So where to use Cp air and where to use Cp gas, is this part clear? So for compression, what is the equation for relating the compressor efficiency and the polytropic efficiency? So this you must have seen in the lecture actually. So I'll just write down the equation. If there's any doubt about the derivation, you can let me know. I'll clear it in the next session. Okay, so this is for a compressor. You have eta c minus 1 by eta c, essentially 1 by eta poly, so eta p of the compressor, into gamma minus 1 by gamma. Okay, so if you just plug in the values here, which gamma will you use? Because we are dealing with the compressor, it has to be gamma air. Okay, so this is this will turn out to be, so you are given the polytropic efficiency, right? So this turns out to be 0.31746. So this definition I hope you all are aware of. Can you just tell me if this derivation is there in the lectures? Is it clear or not? Hello, am I still audible? Yeah, so are you aware of this equation? Oh, okay, the derivation is not done, but the equation is given. Okay. Alright, so this is, you can write eta e expansion for expansion, or you can just write eta t. So I'm writing here eta e minus 1 by eta e, and this is equal to 1 by, okay, now this is the difference in the compression and the expansion part. So in the expansion part, the equation will be eta polytropic, so this comes in the numerator for the turbine, and that into gamma minus 1 by gamma. Now which gamma are we going to use over here? So here it was air, but in the turbine you are going to get the gas because combustion has already happened. So this will be gamma gas minus 1 by gamma gas. Okay, so this you just have to plug in the values. So right now I'll just give you the value, that is 0.22483. Right. Okay, then the next thing is if I just draw the TS diagram again, but and I'm going to use the isobaric lines where I have the constant pressure, static pressure. Okay, so how will the flow look on this TS diagram if I consider only the flow across the fan? Okay, so you have the inlet to the fan. So basically I am drawing the TS diagram for the cold flow, that's all. So you start from this PATM. So help me out with this diagram, come on. What will the fan do? Will the pressure, static pressure increase? Yeah, static pressure is going to increase over here. Okay, then after that, so go back to the diagram. You have this cold flow, and it doesn't have to go through any turbo machinery, but remember it is going to come out of the nozzle. So the cold flow also has a nozzle over here, right? So this is the cold flow going, and this part you can assume is like a nozzle, right? So now maybe you can tell on the TS diagram. So this was from the inlet, and then you went across the fan. Okay, then from the fan into the nozzle. Now how will that affect in the TS flow? So you are going to expand into the atmosphere. So you didn't undergo any combustion, so there is no change in temperature, right? So simply you will draw a line right on top of this coming down back. Okay, that is the exit. So this is essentially what we have to calculate. So first, from the inlet across the fan, we have to calculate the temperature. So I can call this as state 2. Okay, so what is the outlet temperature after the fan? How can we find that? We can use isentropic relations, right? So T naught 2 by T naught 1 is equal to P naught 2 by P naught 1 whole to the power. So what gamma minus 1 by gamma, right? Is this clear? Yeah, okay. And this pressure ratio is going to be the fan ratio which is given to you. So you can find the T naught 2 temperature and tell me. T naught 1 is known. So please just calculate and tell me the value. Yeah, T naught 1 is can you just repeat? Okay, so the answer I've got is 334.34 Kelvin. Yeah, pretty close. Okay, then the next thing we have to calculate is P naught 2. So we have T naught 2 to calculate P naught 2, which obviously you know because P naught 1 is given and you know the fan ratio. So P naught 2 is P naught 2 by P naught 1 is 1.6 and P naught 1 is 1 bar. So of course P naught 2 is 1.6 bar. Now why do we need to check this P naught 2 value? Remember, if the nozzle is choked or whether the exit pressure is more than or less than the atmospheric pressure, that is going to basically define whether there is choking or not. So we have to check if this pressure ratio is more than or less than the critical pressure ratio, right? So we have to compare it with P naught 2 by P naught 1 critical. And this definition, again last time we have discussed what is the definition of P naught 2 by P naught 1 critical. That will depend on, what does it depend on? What are the main parameters that define your critical pressure ratio? Yes, right. So the equation that you have to deal with is 1 minus 1 by eta nozzle, isentropic efficiency of the nozzle, into gamma minus 1 by gamma plus 1. Okay, and this whole quantity is raised to the power of gamma by gamma minus 1. So okay, there is some complex function here. The question is, see, you have to pay attention to these things. What gamma value are you going to use? So now don't get confused. I said that anything below the combustion chamber, that is turbine or nozzle, you have to use gamma gas. But then this flow that we are talking about is through the fan, right? It is not going to undergo any combustion. There is no fuel added over here. So we are going to use gamma for air. Is this clear? Did you understand why we have to use gamma air? Yeah, okay. Okay, so then nozzle efficiency is also given to you and the gamma values are given. So you can find, you'll find that P naught 2 by P naught 1 critical turns out to be 1.96 something. So obviously this P naught 2 by P naught 1, which is actually realized, is lesser than the critical pressure. So there is no choking, right? So I'll just write that down here. So since P naught 2 by P naught 1 actual is less than P naught 2 by P naught 1 critical, we can say that the cold flow nozzle is not choked. Okay. Then let us next we can solve for the nozzle temperature drop. Okay. So what is the temperature drop in the nozzle? I hope this is clear. There will be a temperature drop in the nozzle, so that is very clear in the TS diagram, right? So you are going to come from 2 to E, right? So let us see in the nozzle what happens. The stations can be demarcated once, just for clarity. So let us say this is 2 and the exit is basically, I'm numbering it as 8, or you can just number it as E, exit. Okay, so for the nozzle, the temperature drop is going to be T02 minus T08, sorry, T8 is, so how, okay, before I give the answer, how are we going to get this value? How are we going to get this value T8? We just have to get the temperature at the exit of the nozzle. So how do you get that? Yeah, come on, this we've done several times. By isentropic relation, what will we get? So we know that okay, we know that P02 by P01 we know, right? So from there you have got T02 by T01. That is the isentropic relation you have used. So now what can you do? How are you going to get T8? Okay, what happens to the stagnation temperature in the nozzle? That is the first question. What happens to stagnation temperature? Can I say T02 is equal to T0E? Can I say this? So in a nozzle you are not having any turbo machinery again. So the stagnation pressure and the stagnation temperature will remain same, right? Yeah, okay. So we are going to use the definition of the nozzle efficiency. And how is nozzle efficiency defined? What is the definition of nozzle efficiency? You remember that if you are coming, this is your real path, but ideally you should have come isentropically. So you will say the actual temperature drop by the ideal temperature drop. That's how you define the nozzle efficiency, right? Yeah, so this I'll just write over here, actual delta T by ideal delta T. Okay, so basically using this definition I can get T02 minus T8 is equal to eta nozzle into T02, 1 minus is going to be T01 by T02. Okay, T0, so I'll just write T01 by T02. So that further you can get from the pressure ratio because you know it. So that is going to be 1 by the pressure ratio of the fan to the power gamma minus 1 by gamma. And again gamma you will use for air. So this is gamma air. Okay, now using this simple relation you will get the value of T8. Did you understand what have we done over here? We have just used the nozzle efficiency and then the temperature ratio we have got from the pressure ratio. Okay, so the value of T8, can you evaluate and tell me the value of T8? So first you can just evaluate T02 minus T8. That turns out to be 39.91 Kelvin. Okay, and T02 was known to us over here, which is 334.34 Kelvin. Okay, so you can get T8 is 334.34 minus 39.9. am I still audible? One of you just give me the values. Okay, 294.4. Okay, thank you. Okay, so now what is the next step? So once we know the temperatures, we can find the velocity, because remember we have to find the thrust that is produced by the cold nozzle and the thrust produced by the hot nozzle. So for that we need the velocity of the cold nozzle, that is flow coming out of the cold nozzle. We have to calculate that velocity. Okay, so let us denote that cold flow exit velocity as C8. Okay, so C8 is nothing but 2 Cp delta T across the nozzle, which is T02 minus T8, which we have evaluated above, and under root of this. Right, now what is Cp over here? Cp again is Cp air, because this is just the cold flow. So what is the velocity that you are getting? Are you guys doing the calculation? Yeah, 283.24. Okay, this is the value I have here. Okay, and then you can calculate the mass flow rate. So remember, we have been given m dot total. So m dot total was given, and the bypass ratio was given. So you can find out m dot c. So m dot c is nothing but m dot total into b by b plus 1, right? And this turns out to be 175 kg per second. Okay, so now it is very easy to calculate the thrust due to the cold flow. So I'll denote this as T cold. This is nothing but, so what is thrust due to the cold flow? What is the expression? Yeah, m dot c into C8. Yeah, basically it's m dot UE, right? So this is yeah, so what is the value in newtons? You can give me the value in newtons. You just have to multiply these two things. So yeah, it's 49567 newtons. Okay, so we have completely solved the cold flow. Now what is the next task? We have to solve it for the hot flow, that is the flow through the core, or the that is going through your compressor and the high pressure turbine, combustion chamber and all that. Okay, so maybe I'll just change the color here so that it's clear. Okay, so let's now do the calculations for audio fine. You getting a fine audio? I just lost connection. Okay, yeah, so let us do the calculation for the hot flow now. So I'll just write that here. So we are given the compressor pressure ratio. No, we are given the overall pressure ratio, and we are also given the fan pressure ratio. So overall pressure ratio is nothing but fan pressure ratio multiplied to the compressor pressure ratio, right? So we can find the compressor pressure ratio from here, which is P03 by P02. So what is 3 and 2? So come back here. So this is now just after the compressor would be state 3 combustion chamber, over here state 4, and then after the turbine would be 5. Okay, so Compressor pressure ratio is what? What is the value? 50. That's it. Okay, then we can find T03. So we can just simply use the isentropic relations, right? That is T03 by T02 is equal to P03 by P02 to the power gamma minus 1 by gamma. What gamma will be used here? Now we are in the hot flow. So what gamma will be used here? Sorry? No, you'll not use gamma of gas. Why will you use gamma of gas? So you should use, we have only reached compressor, right? Still you have not added the fuel, so you should use gamma air over here. Yeah, so just be very careful while doing this. You should see at what stage you have reached. Okay, now okay, ideally if you have you remember we evaluated this exponents, sorry, we evaluated these exponents eta c minus 1 by eta c, eta e minus 1 by eta e. So ideally we should be using these values, because what is given in our pressure ratio, we should raise that to the power of okay, here instead of gamma we should be using this value, that is because now we are having this twin spool configuration, right? And what is given to you is the polytropic efficiency, so that you have to incorporate in your equations. So I hope this part is clear from the lectures. Yeah, okay, so now you have the value of this eta c, and you also have the pressure ratios. So while calculating this eta c also, remember we have used gamma air and not gamma gas. This is very important. Okay, so now you can find the outlet temperature of the compressor, that is T03. Can you tell what is T03? T02 will be the same what you found in the cold flow, right? Yeah, it's okay. I have 789.86, so that's, yeah, approximately 790. Okay, so that's T03. And then in the turbine, remember ideally we should have P03 is equal to P04, but in the combustion chamber we said there is some pressure loss, so this is ideally, but there is some pressure loss, so that is given as delta P, which is nothing but P03 minus P04 by P03, right? So if you go back up, you are given a combustion pressure loss of 1.5 bar. Okay, so this is not a fraction. What is given is the actual value. So you are just given P03 minus P04, which is 1.5 bar. So you can just find the value of P04, and once you know P04, you can calculate. Okay, I've written it in the wrong place. Yeah. So you can find P04, and once you know P04, you can find you can do the calculations for the turbine, right? So what is P04 value? And T04, if you remember, is already given to us. What is P04? Sorry. Yeah, T04 is 1500, but what is P04? You can just evaluate it. is P04? Anyone else can answer? Yeah, 22.5 bar. Okay, then we can find the temperature at the outlet of the high pressure turbine. So let us now do the calculation for high pressure turbine, which is so the outlet is the station 5, right? So I can write T05 is equal to T04 minus, this is CPA by eta mechanical, or you can say eta spool. So here we have denoted as eta mechanical, Cp gas into T03 minus T02, right? So how did we get this expression? Before you solve it, how did you actually get this expression? Right, so work of the high pressure turbine multiplied to the transmission efficiency, which is nothing but your eta mechanical, should be equal to the work of the compressor, right? And what is work of the compressor? It is, see, in compressor it was air, so you have Cp air into T03 minus T02, okay, and here you have eta mechanical multiplied to now in the turbine you have the gas, because combustion has already happened, so you will have Cp gas, and that multiplied to basically to be T04 minus T05. Okay, so if you just rearrange this, you will get that equation above. Okay, so what is the value of T05? Okay, yeah, so that's right. Okay, then what is the outlet pressure, or how will you find the outlet pressure at the high pressure turbine? How will you find P05? So what is the relation between P05 by P04 and T05 by T04? So given you are given the polytropic efficiency, and then remember we found that coefficient, we basically found this eta E for expansion, so that you will use here eta E by eta E minus 1. Okay, is this relation fine? Yeah, okay, so what is P05? What is the value of P05? I'll just give the value right now, 5.59 bar. In case you get anything different, just stop me. I'll move on to the low pressure turbine. So are the others also calculating, or just one person is doing all the calculations? Are you guys following the solution or not? Yeah, can you repeat? Okay, so the low pressure turbine you can again calculate in a similar manner. So you can find for T06, so I want to find T06, right? So how do I do that? I can just evaluate the work of the low pressure turbine multiplied with the eta mechanical, and this will be the, what will this give? So what does the low pressure turbine do? Yeah, right, it is the work that the fan requires. Okay, so if you just do this calculation, and for work of the fan we have calculated all the things in the cold flow. So if you just put in the expression and rearrange a little bit, you will get this. T06 is nothing but T05 minus the bypass ratio plus 1. So remember that, okay, maybe I should go step by step. Okay, so what is the work of low pressure turbine now? Cp gas, okay, multiplied to the temperature difference is T05 minus T06, okay, and again you have eta mechanical, but how much air is going through this? M dot H. And what amount of air is going through the fan? Is it M dot C? Yeah, it is total. So you should see very carefully what is happening here. So after the fan there is M dot C and M dot H separate, but what is coming in? What is coming in is M dot H plus M dot C, and the whole, this total mass flow is going to go across the fan. So the fan is going to do work on the total inlet mass flow rate. Okay, so that's why on the right hand side you are going to have M dot H plus M dot C, and that multiplied to Cp air into T02 minus T01. Okay, so this you can just plug in the values and get the value of T06. So since we are running out of time, I will give you the values, and I would request you to do the calculation after the class and verify if you get the same answer or not. Okay, so T06 turns out to be 851.33 Kelvin. Yeah, okay, you've got, great. And then how will you evaluate the outlet pressure across the low pressure turbine? So again you will use the same technique. P06 by P05 is equal to T06 by T05 to the power of this eta E by eta E minus 1. Okay, so now you have T06, T05, and you have P05, so you can find P06, and P06 turns out to be 1.811 bar. Is this okay? Yeah, okay. So now we have the pressure ratio for the hot nozzle, right? So for the hot nozzle, that is nozzle through which the hot flow is going, we have the pressure ratio actual, which is P06 by ambient pressure, right? So we are going to expand to the ambient pressure. So the actual pressure ratio, it turns out to be this 1.811. Okay, now we have to evaluate what is the critical pressure ratio. Why do we need to evaluate this? To check if there is any choking, right? So for the critical condition, again we have that equation, same equation, 1 divided by 1 minus 1 by eta nozzle isentropic efficiency here, gamma minus 1 by gamma plus 1, and this whole raised to the power of gamma minus 1 by gamma. Now tell me, what gamma will you use over here? So when we were doing it for the cold nozzle, we used gamma air, but for the hot nozzle, what is the fluid that is coming out? It is the air plus the fuel which has undergone combustion. So that is going to be the gas. So here you should use gamma of gas. Okay, and the nozzle efficiency remains the same. It is given same for both hot and cold nozzles. So you can evaluate this, and P06 by PA critical turns out to be 1.918. So what do you conclude now? Given the actual and the critical pressure ratios, what do you conclude? Yeah, there is no choke. So the hot nozzle I'll just say no choke. Okay, so now because there is no choking, we can then evaluate the velocity, right? Okay, so for velocity, again, what do we need? We need the temperature at the exit of the nozzle. So how do we find the temperature at the exit of the nozzle? Let us say that is T7. Okay, so we can find T7. How do we find T7? So we just did this same thing for the cold flow. So you should be able to answer now. We have to find the temperature at the exit of the nozzle. How do we do it? Yeah, exactly. So you use the definition of the nozzle efficiency, and you can write the expression as T06 minus eta nozzle into T06 1 minus, here ideally you will have the temperature ratios T01 by T06, and that you can replace with the pressure ratio, which is P01 by P06 to the power gamma minus 1 by gamma, and be careful to use gamma gas over here. Okay, so you can evaluate T7, and that turns out to be 739.817 Kelvin. Now that we have the value of this temperature, we can simply find the speed. So I will call the speed as C7, which is the hot flow speed. So C7 is what? 2 Cp gas into T06 minus T7, this whole to the power of half. Okay. So C7, is this formula clear? I hope this formula is clear, how you get the, yeah, okay. So C7 is 505.99 meters per second. Okay, so next we can evaluate the thrust. So what is the thrust? I'll write this as T1. This is thrust due to the hot nozzle. So how will you evaluate this? What is the expression? What is thrust? So previously also we have done. Yeah, so it's simply m dot h multiplied to C7, and m dot h is what? It is the total mass flow rate. So m dot total into 1 by b plus 1, and then you have C7. So if you just plug in all the values, the force turns out to be 17709.7 newtons. Okay, so now what is the total thrust also you can find. So total thrust is just the thrust due to the cold flow plus thrust due to the hot flow, and that is approximately 67276.7 newtons. Is this what you are getting? Yeah, okay, you got this. Okay, now if you go back to the question over here, the last thing they have asked you to evaluate is the specific fuel consumption, and they have also given you the fuel air ratio. So what is the specific fuel consumption then? Right, so SFC is nothing but fuel air ratio divided by the total thrust, right? So fuel air ratio to you is given to you as 0.0223, and we have found the total thrust also. And okay, this is T by m dot. What is SFC actual definition? It is m dot F by thrust, isn't it? Yeah. So then what m dot will you use over here? M dot total. So T by m dot total you can use, and SFC turns out to be 0.042. Okay. Yes. Sorry. Unit. Yeah, unit here is kilogram. Wait, it's there in the questions. Yeah, it's kg per hour Newton. Okay, then I guess so the definition ideally, I mean, so in the solution what I have is total, but ideally this should not be m dot total, it should be m dot h. So what if you plug in the value of m dot h and evaluate and tell me? Okay, so there is another way to you can just avoid all this confusion. Okay, so let's do that. So let us write this as m dot f by the thrust total. Now tell me what is m dot f. M dot f is fuel air ratio into m dot a. And what m dot a will you give over here? We'll say I'm burning the fuel in the combustion chamber, right? So in the combustion chamber, the amount of air that I get is actually m dot h, right? So I would write m dot f is f into m dot total by b plus 1. So if you use this now, are you getting the correct value of SFC? Hello? Okay, so what is the m dot f that you are getting? If you just evaluate m dot f over here. No, what units are you using? So I guess the units are different. Have you seen this is kilogram per hour? Okay, so m dot total was given to you in what units? Kilogram per second, isn't it? Yeah, so then you should probably convert it to the right units and then compare. You got it, right? and that is if you use, yeah, you will have to use over here the mass flow rate of the hot flow, right? Yeah, right. So this would, yeah, this is what even I think is correct. Okay. Yeah, so you should pay attention to the units.